I'd like to talk for a bit about temperature, because temperature is one of these environmental challenges that organisms face in a lot of different ways, and they have a lot of different means of dealing with it. Okay, what physiological effects does temperature have on an organism? Well, a lot of things, even down at the cellular level, change as temperature changes. So enzyme kinetics change. Chemical reactions accelerate as temperature goes up. They decelerate or slow down as temperature goes down. Membrane permeabilities change. In general, membranes get leakier as temperature goes up. The rate of diffusion also depends on temperature. As molecules start vibrating around more rapidly as temperature rises, that tends to allow diffusion to happen more quickly. So these really fundamental molecular and cellular properties change with temperature, and that's going to affect any organism that is exposed to a temperature change. If temperatures get too extreme, you can have really radical changes. As I mentioned before, if you get a fever that's more than a few degrees above the normal human temperature, it will actually start damaging the folding of some of the proteins in your cells. If this happens more severely enough for long enough, your cells will begin to die. At the other extreme, at low temperatures, liquids start becoming solid. This has the effect of ripping apart cells as ice crystals form, but actually, more importantly, what it does is that as liquids freeze, they exclude whatever molecules were dissolved inside them. And so you have sudden dramatic changes in concentration within cellular or intracellular, or extracellular fluid. And that often will screw up everything about a system if you change the concentrations very dramatically. In general, most organisms have a range of temperatures where their function is optimal, and it can be fine-tuned to a different environment. So for example, here's a moss that photosynthesizes best at a rather cold temperature. A desert shrub, on the other hand, might photosynthesize best at a temperature that's well above our body temperature. Our body temperature is down here at 37 degrees. Organisms can be adapted to deal with temperature in different ways besides having different optima. In particular, there are two basic strategies of dealing with temperature that you're probably already very familiar with. One of them is called being warm-blooded, and the other one is cold-blooded. You can see here with these infrared photographs that this dog over here is shedding a lot of heat, whereas the scorpion is the exact same temperature as its environment. Technically, a better term to use than warm-blooded is homeotherm. A warm-blooded organism is referred to as a homeotherm. Warm-bloodedness is referred to as homeothermy. The reason that that's a preferred term is that homeo means the same. So these are organisms that tend to maintain the same internal body temperature. And that's what really matters, is not that they're warm-blooded, but that they regulate. The technical term for these temperature conformers over here are poikilotherms. Those are organisms that allow their temperature to drift dramatically. Obviously, though, some organisms that don't generate their own internal heat do have ways of regulating their temperature. So it's not as though any particular organism is going to fall completely into the homeothermy end of the spectrum or completely into the poikilothermy end of the spectrum. Most organisms regulate their temperature to some degree, and most conform to some degree. Let's look at some of the ways that organisms do this. One efficient way of looking at or thinking about the different mechanisms that affect an organism's temperature, and therefore the mechanisms by which it can regulate its temperature, is to look at its heat budget. So the total heat budget of an organism consists of 5 different terms. In other words, there are 5 different ways that you can heat an organism up or cool it down. Metabolism is one of the mechanisms that affects temperature, body temperature. And really, metabolism can't cool an organism down. It can only heat it up. Warm-blooded or homeothermic organisms create a lot of heat by basically just cycling protons through the membranes of their mitochondria without capturing the energy that results as they do this. That energy is then dissipated as heat. That heat has the side effect of warming up their tissues. It's tremendously wasteful, but it allows us to bring our tissues up to a particular temperature and keep it there. By regulating our metabolism, we manage to regulate our internal temperature. There are, however, a bunch of other parts of the heat budget that you need to take into account, and these apply to all organisms. One is conduction. One thing that an organism can do to change its temperature is behavioral. It can come in contact with something that is warmer or colder than itself. Conduction is the transfer of temperature or transfer of heat between two solid objects. So for example, this agama lizard is basking on a rock. Partly it's that it may be that it is receiving radiation from the sun, so there's radiative heating going on. But part of the advantage to flattening itself against this rock is that the rock has been sitting in the sun for a long time, and it is warm enough that the lizard can absorb a lot of heat from it. Convection is another process that affects temperature. Convection is when you have a moving fluid or gas moving around a solid object, and that moving fluid or gas can transfer heat into the object, or it can take heat away from the object. You are probably most familiar with this in the form of wind. When you're out in the wind, assuming that the air is colder than you are, it's going to feel much colder than if you were out in a still windless day at the same temperature. So wind chill is very important in cooling you down. I have a few times been in a situation where there was very windy and it was warmer than my body temperature. This sometimes happened in the town of Davis, which is where I went to graduate school. Every summer there'd be a few days in which you go outside and it just felt like you were living in a hairdryer. The wind was actually warming you up rather than cooling you down. Again, this is something that organisms can deal with behavioral changes. One thing that we often try to do is we try to get out of the wind. But there are also anatomical changes that you can take advantage of in order to cut down on convective heat gain or heat loss. One of those big differences is fur. By establishing a boundary layer of still air close to an organism, this, like say this buffalo, the buffalo dramatically reduces its convective heat loss. There's also radiative heating to deal with, and this is something that you can see with these infrared photos. All organisms radiate heat to their environment, and all organisms' environments radiate heat to them. As you can see, the hand of this particular homeotherm is radiating off a lot of heat, whereas the body of this poikilotherm is radiating off very little heat. Radiative heat is largely a matter of whether or not you are hotter than your surroundings or whether or not you are sitting in the sun. Obviously, organisms that sit in the sun like this lizard are going to get quite a lot warmer. You can see that this lizard has a temperature up here in the orange range, whereas this one is down here in the blues and purples. In some cases, organisms that are basking get so much radiative heating that their temperature can exceed that of what we think of as a warm-blooded organism. And again, this is a behavioral strategy that organisms can take to maintain their internal temperature or control their internal temperature. Finally, There's the process of evaporation. When water makes the transition to a gaseous state, to water vapor, it absorbs heat energy from its surroundings. And there are all sorts of organisms that take advantage of this. We sweat, so we can take a great deal of advantage of evaporative cooling. Although one of the risks of this, one of the trade-offs of this, is that we can use this mechanism enough that we actually become dehydrated. But there are a lot of other organisms that you may not think of as using evaporative cooling that nonetheless do. When it's really hot out, you'll see birds pant. Dogs pant a lot. The reason they have such big tongues is that they're using that surface area, that wet surface area, to get rid of a lot of heat due to evaporative cooling. But other organisms, like, say, this marine iguana, do what maybe you've done in the heat of the summertime. You jump in the water and then get out, and the evaporation of the water cools you off. When you put together all of these terms, you get the heat budget of an organism. And so you can see that while we think of warm-blooded organisms as being the ones that regulate their temperature, metabolism is only one way of regulating temperature. Most organisms, even the ones we think of as warm-blooded, use a lot of different mechanisms in homeostasis. Not just physiological ones, but anatomical ones and behavioral ones. I do want to point out that, however, although we've talked about the array of regulatory mechanisms that organisms can use to regulate their temperature, there are also ways in which even homeotherms conform to the outside conditions. And this is true for most organisms facing most environmental variables. Most organisms regulate their internal environment within limits, but they let it drift within those limits so that they're not spending quite so much energy and other resources in regulation. So, for example, camels, which of course inhabit desert environments, allow their temperature to drift. This is the internal core temperature of a camel. Obviously, it lets it drift down at night and then up during the day, down at night, up during the day, and so on. These are rectal temperatures of camels taken many, many times over several days, and I pity the person who had to do that job. I also pity the camel because what they did next is they let the camel get dehydrated. And you'll notice that the temperature swings get much wider. Because when an organism is dehydrated, it has less water. That has less thermal inertia. Less water means less thermal inertia within the body of an organism. And so they allow their temperature to drift much more widely. So the conformation versus regulation that a camel participates in depends partly on its physical makeup, how much water it's got, but also it's strategic. This camel can save a lot of energy and water by allowing its temperature to fluctuate a lot from day and night. And you'll see this same pattern in a lot of organisms that are supposedly homeotherms or temperature regulators. Here's another example of this incredibly cute organism called the fat-tailed lemur. Here it is with its chubby, chubby tail. That's because it keeps fat in its tail rather than insulating its body. And as a result, it goes through these wild temperature swings every day. There are a number of organisms that if they have slow metabolisms, they'll allow their temperature to drift. One of my favorites is the three-toed sloth, which has to bask in the mornings to warm up enough to feed. And again, on the other hand, there are a lot of supposedly cold-blooded organisms that can and do regulate their temperature. For example, bumblebees and hawk moths, by shivering their flight muscles, can warm their bodies up above the temperature of your hand. If you actually catch a hawk moth after it's been flying and you hold it in your hand gently, you can feel the heat coming off of it. It's hotter than you are. But they also have mechanisms for regulating their temperature so that they're the optimal temperature for flight. The take-home message from all of this information about temperature is that there are a lot of different mechanisms for homeostasis. You'll be seeing mechanisms for homeostasis that are physiological, that are anatomical, that are behavioral in all sorts of organisms, and that there's a whole spectrum between conformation and regulation, which is governed by trade-offs that an organism faces, the physical trade-offs as well as trade-offs that may depend on its environment.